Welcome to the deep dive. Today we're tackling a really counterintuitive idea from mathematics, the Weierstrass function.
It's a fascinating one. Definitely turns some common ideas on their head.
Right. Our goal is to unpack this function. It's continuous everywhere you can draw it without lifting your pen, basically. But, and this is the kicker, it's differentiable nowhere. So for you listening, that means you can't actually find a tangent, a slope, anywhere on this curve. It's just infinitely jagged.
That infinite jaggedness, that's precisely what caused such a stir. When Carl Weierstrass published his example back in 1872, it was a real shock.
A shock. Why specifically?
Well, the prevailing wisdom in the 19th century, even among giants like Gauss, was that continuity implied differentiability, except maybe at a few isolated points. People relied on their geometric intuition, smooth curves.
Okay, so this function just shattered that intuition.
Completely. You have prominent mathematicians like Charles Hermite calling these kinds of functions a lamentable scourge.
Wow, a scourge. That's strong language for math.
It really shows the resistance. They saw it as a kind of mathematical monster, something that shouldn't exist. It actually took quite a while for the idea to be widely accepted.
How long?
Decades, really. Acceptance grew mainly in the 20th century, partly because computers eventually let us see these things, roughly.
Visualization helps.
Definitely. And also, crucially, because practical applications started popping up. Things like modeling Brownian motion, the random jiggling of particles. Nature, it turns out, needed these infinitely complex, jagged functions.
That's incredible. Reality catches up to the monster. So how did Weierstrass actually build this thing, if it baffled the greats before him?
It's built using an infinite sum, specifically an infinite Fourier series involving cosine waves with certain conditions on A and B.
Okay, an infinite sum of waves. How does that make it jagged everywhere but still connected?
It's a delicate balance. The A term, where 0 and 1, makes the amplitude of each successive wave smaller. So the terms themselves are bounded, they shrink.
Right, so they add up to something finite. That gives you continuity.
Exactly. The series converges uniformly, thanks to something called the Weierstrass M-test. That guarantees the function is continuous, no gaps, no jumps.
But then how does it avoid becoming smooth?
That's the B term. B is a positive odd integer, and importantly, the product AB needs to be greater than $1 plus fractal 2. This makes the frequency of the waves increase very, very quickly.
So faster wiggles pile up.
Much faster. The waves oscillate so rapidly that the shrinking amplitude never gets a chance to smooth things out locally. You zoom in, and there's always more oscillation, more jaggedness. Between any 2 points, it never settles into a straight line or even a simple curve. Never monotone.
Infinite detail. Which sounds a lot like
fractals, yes. In modern terms, the Weierstrass function is one of the very first fractals ever studied. It exhibits self-similarity. The complexity looks the same no matter how much you zoom in.
That fractal nature is key. Now, you mentioned Weierstrass wasn't maybe the absolute first person to think about something like this. What about Riemann?
Ah, yes. Riemann described a similar function earlier using sin and 2,2. He claimed it was nowhere differentiable. But later analysis showed Riemann's function actually is differentiable at certain specific rational points, very specific ones, related to the Puppe point, so it's differentiable almost nowhere, you could say.
I see. A subtle but important difference.
Very important. Weierstrass provided the first proven, rigorously demonstrated example of a function that was truly, strictly differentiable nowhere, no exceptions.
So, wrapping our heads around this, is this function just a mathematical curiosity? A pathological case, as they used to call it? Or is there something deeper going on?
That's maybe the most profound takeaway. While it feels like an exception, like a monster, in the grand scheme of all possible continuous functions, functions like Weierstrass's are actually typical.
Typical. How can that be? The smooth ones seem so normal.
Mathematically, in the space of continuous functions, the set of nowhere differentiable functions is what's called comeager. It's topologically dense. It means, in a sense, that most continuous functions are like this. The smooth, easily drawable ones we learn about first. They're the rare exceptions.
Wow. Okay, that really flips the script. Our intuition about smooth lines is actually misleading us about the general case.
Precisely. It was a fundamental shift in understanding the relationship between continuity and smoothness in mathematics. Geometric intuition is powerful, but it has limits.
A truly deep dive today. Before we finish, just a quick note that this deep dive is brought to you by embersilk.com. Embersilk is the answer for all your AI education and integration needs. Check them out.
A valuable resource.
So a final thought for you, the listener, to ponder. Those incredibly rapid oscillations we talked about, the wiggles getting faster and faster, that's not just a detail, it's the guarantee. It ensures the slope is changing so violently, so infinitely often, that it can never actually settle down to define a single tangent line anywhere.
It's a structure born from controlled chaos, you might say.
Perfectly put. Thanks for joining us on this exploration. If you found this dive into mathematical rigor interesting, please do subscribe and maybe leave us a 5-star review. It genuinely helps us bring more deep dives like this to you.